Welcome everybody after the coffee break. We will now have a presentation, Keykeriki, Universal Wireless Keyboard Sniffing for the masses, by Thorsten Schröder and Max Moser from Remote Exploit. I'm looking forward to it.
Yeah, good morning.
Morning, everyone. We will talk today about wireless keyboard sniffing, obviously. First of all, I have a small warning slide. Analyzing someone's data transmission could bring you to jail in some countries. So you're just allowed to verify your own security of your transmission of keystrokes, for example. What is this talk all about? We had quite a few talks on that topic, but we had some major improvements during the last few days, really the last few hours especially.
Last night.
And so we are able today to, let's say, talk about the current state in the various transmission techniques used by wireless devices, starting from 27 megahertz based radio transmission on older devices over Bluetooth. Just some slides on the topic of Bluetooth till the proprietary 2.4 gigahertz based cheap devices, which actually replace the old 27 megahertz.
Yeah, this talk is about the current project state. As we told you before, we didn't finish yet the entire project yet. So it's still work in progress, and we are happy to have some cool stuff to show to you. We are able to show how we can send keystrokes to 2.4 gigahertz receivers, and we will talk about the gigahertz stuff later. Yeah.
So about the evolution of the keyboards, a quick overview. Wireless keyboards started with that infrared stuff. Maybe you have seen it in your room upstairs in the hotel for the TV system. It seems to be an infrared device. The problem with that is obviously line of sight requirement. So they replaced it with a cheap transmission technology. That's the 27 megahertz based ones. They are extremely cheap. You can extremely build cheap transmitters and receivers, and it's quite well known. 27 megahertz is in the range of the same frequency band as citizen band, so 11 meters. And next was the evolution to the Bluetooth keyboards. We'll tell you something about it, but in general, those keyboards were quite much hyped in the early days, but there are only a few vendors which actually sells them. Logitech has some keyboards available. They are all quite expensive. Yeah, and they looked for a better alternative, which is cheaper and easier to use. So they go back to a simple transmitter scenario in the proprietary 2.4 gigahertz one. So first, about 27 megahertz. There's one important thing in here. It's a pure one-way communication in all the implementation we have seen so far. So there is an obvious problem. This was already posted to Bugtrack in 2001 by a company called Datentreuhand. They found out if you buy two identical receivers and you hit connect on them, so to bring the receiver into the state where he can interconnect with the keyboard, and you press the connect button on the keyboard, both receiver will receive the keyboard key, and so both will receive then the keystrokes. So that's the simplest attack scenario in all the implementation we have seen so far. This works really for all the old vendors. The problem is you have to force the let's say, target to do a resync during a defined time frame where you are waiting there with your receiver. So it's not that practical. You can jam him so he tries to reconfigure it, but I mean, there are better options. So we were analyzing the signal because we did not have a clue what is going on there. And on all the implementation, we found some Miller or delay encoding in place for putting the binary data onto the frequency. This was quite new for me, and it took us good of a headache because Microsoft, let's say, made a variation of the symbols behind the Miller encoding. So it looked at first quite okay, but at the end, the data was completely messed up, and it took us some time to analyze that. But it's straightforward, so you have some kind of a compression in there and a pretty obvious signal pattern, which basically is typical for Miller. It's that you have a signal period of 1, 1.5, and 2. That's pretty unique. And yeah. That's
a really early stage of research when analyzing and reverse engineering this protocol. Analyzing the signal and find out how the signal works actually.
Exactly. After we were able to understand what is going on there and what type of encoding it is, we just looked at the patterns during the transmissions, and you can clearly see if I press 3 times an A, for example, on a keyboard, you can see some patterns 3 times. If you zoom in, we were able to see that, for example, that's Logitech, that each keystroke consisted out of 2, basically retransmission. It's quite fun that older versions of the keyboards transmitted 3 times, newer ones are using only 2 repeatings. So there is some kind of a backward compatibility guaranteed by that. Yeah, by understanding the patterns in there, we were able to basically decode the data and get some binary tables out of it. We just added the Logitech ones here. There is another table for Microsoft, but we presented it already on different slideshows. But for Logitech, it's quite obvious. You can see that some parts of the table are changing when you press a key down or a key up. So what's noted there in the state, you can see that always when I press a key down, there's a 1. And if the key is released, it's a key up. So on the state field, you can see it's up or down. Then you have some parts which change when you change the keyboards, and some parts which will change when you have a keystroke. So that's basically all the process on the different vendors. So we analyzed first signal, then encoding. Luckily, it was always Miller. And then just analyzed what is in there, what's not. It's quite fun that Logitech transmits it in clear text, except you add some additional, let's say, software encryption. So you have to install a specific driver. Then you have to type some password which is shown to you on the screen, and then you have an additional encryption in place. We did not look at that one. For Microsoft, it was quite easy.
It is the same,
yeah. They did not transmit it in clear text. They transmitted it encrypted. They had a 1-byte XOR key. The hardest part was actually not depending on sniffing the sync signal, instead of knowing what language is the target actually typing. And just as a side information, we came up with the idea. As you have a key and you have a value, if you XOR them, you always get the same result when the same key is pressed. So we came up with the idea of using www dot as an identifier that 3 times the same key was pressed. Yeah. And if the dot was pressed after the 3 identical transmitted packets, we assume that we have the right key.
That's how our device works. So we didn't introduce the Keykeriki key device yet. So it's the small PCB here. We built an own receiver and for the wireless keyboard stuff for 27 megahertz, and yeah, we wrote the software to crack the XOR key for Microsoft keyboards on the fly by performing some kind of a statistical analysis of the crypto which goes through the air. yeah, and that's what he told. So we assume that the user is used to type www dot, or for example, start with capital letters at the beginning of a sentence. And that's, yeah, the meta characters are not encrypted, and that's why we are able to perform this analysis on the fly on this small device, which is based on an AVR 8-bit microcontroller. So it's quite simple.
We don't go into deep on that 27 megahertz thing and Microsoft because it's quite well documented, and we wanted to show you the new technology at least in more detail. But finally, we have implemented also the Logitech protocol during the last few days, so we are now able to show you that it's working actually. The Microsoft was there.
Our goal was to build an own device to be able to connect a real antenna to our device, so we can maybe receive keystrokes and all the stuff from a bigger distance. So Microsoft guarantees to be able to receive those keystrokes within 1 meter, and yeah, we are able to receive keystrokes like 5 or 10 meters.
Depending on your antenna?
Depending on the antenna, right? That was the main problem in this 27 megahertz, 11 meters band. The antenna is quite huge. That's why we also had our focus on 2.4 gigahertz, because the antennas are quite small.
We don't go into detail on the let's say firmware itself, but it's
yeah,
the firmware
this
itself.
is the user interface.
Yeah.
If you connect using your USB serial cable, the Keykeriki device is USB powered, and you can also use the device using the serial console. So this is a small menu.
The menu and the whole, let's say, usage is implemented into the firmware, so you just need basically a serial terminal to connect it. And for example, you can check the configuration of the system. You can switch on signal strength monitoring when you type something. Yeah, there is a possibility to add an SD card into the device, so all the keystrokes get logged.
So we can use 2 gigabyte SD cards for saving and storing all of the keystrokes in RAW format, so encrypted, and also the plain text data is also stored on the SD card for later analysis.
Now it's rebooting again. The TRF chip, which is actually the receiver chip, is capable of capturing two channels. And yeah, we were able, using the firmware, to switch to the channels, and it's quite fun that the chip actually implemented all the common frequencies in one chip. Yeah. Okay. Now, just for the Logitech, I just have the keyboard here, and yeah. Wow, this seems to be working. Logitech is not transmitting any encryption, so this is quite straightforward. One special behavior of Logitech is that they switch channels on certain time, or if you press the button, they will switch channels. I guess that's just for not interfering with other keyboards inside the same room. So it's quite straightforward, just typing and the receiver will get the result. Because this was kind of cool, but we wanted to have it without a computer. We built a small battery pack, but we had a small problem today.
Battery cells are almost done.
Empty. So I have to power it using USB now, but just to give you an idea what you can do, there is an additional UART available, so you can connect anything that understands UART, basically a serial connection to the Keykeriki. You power it up, and
we also tried to connect an iPhone to the Keykeriki device, for example, to see all the keystrokes on the iPhone device, but we had some trouble.
So, for example, here I built a small LCD device, or not that small, but an LCD device. And if I type now here, you should yeah, you should see keystrokes. So, I mean, together with the battery pack, that's quite fun. And this scares even my mother, so you don't need actually a computer to visualize what's the threat behind of it. And, I mean, you can replace that LCD with a handy and using it as a modem, for example. Then you just have to modify the firmware a bit, and when it's writing the character there, it's transmitted over another protocol, so kind of a replay, actually.
That's why we call it universal keyboard sniffing device.
Yeah, restrictions in 27 megahertz. It's obviously the antenna. 11 meters is the best, let's say, full-size antenna of the wavelength. That's a real problem. You can take smaller ones. I have here a PCB antenna connected to it, and it works, but the range is quite limited. But that's not only a problem of the antenna. We started to implement the signal capturing, let's say, the wrong way around. So actually, we did not implement the error correction properly, so we lose immediately
still
keystrokes.
work in progress.
Yeah.
Yeah.
As soon as we have the error correction in place, we expect, even with cheap antennas, it's extremely improved. But that's not really the problem, because we have an SD card in there. It's quite small. You can add a battery pack and put it somewhere for testing your security. So, I mean, there is the limitation of the size, but it's okay, let's switch over to Bluetooth. I guess it's just 3 slides. I don't want to talk about the vulnerabilities available in Bluetooth and what was possible with injection and stuff like that, but just give you focused on keyboards, what's going on there. Bluetooth is extremely popular, or at least in the mobile world, so everyone knows that. The main difference compared to different other transmission techniques is that the security mechanism aren't, let's say, accessible for the developer or for the operating system, because it's realized already on the transmitting device within the firmware. So it's, if it's badly implemented, the developer cannot do a thing about it, except adding an additional layer on the application. So all the stuff which is important, pairing process and the encryption, key exchange, is handled by the device itself. This makes the requirements on the device, on the transmitting device, quite a bit higher, so it's quite expensive to develop that chip or transmitter compared to another technology. Another thing is it's hopping quite often within the frequencies, so this makes it quite, let's say, hard to sniff without a huge amount of money available for a private person. Yeah, that's the major drawbacks, I guess, on Bluetooth. It's too expensive. That's why only a few expensive keyboards are available on the market. Then sniffing is possible. So if you have a frontline Bluetooth sniffer, you can sniff it using the Windows software. Or if you find on the internet the demo version, there is a firmware inside of it, which you can flash onto your Blue Core 3 CSR dongle, and then you can use a public available tool which basically reads out all the information needed to crack the pin. Simple pairing should fix that by changing the key exchange handling. But the problem in most Bluetooth bugs was basically a buggy implementation. So you can inject stuff without encryption, or you can add some hidden channels. So the implementation was quite often quite buggy. So this is what it looks like when you sniff it. So the first window is basically the frontline.c or CSRC code sniffing for that information. It gives you the command you have to copy into the other window and start the pin crack, and then you have the pin, and then you can actually listen to it or associate with it. So it's basically done, but the problem is you have to sniff during the pairing process. That's the current state, as far as I know, and which is relevant to the keyboards. So
So, okay, the next and most modern kind of wireless keyboard is based on a proprietary 2.4 gigahertz technique. The most devices we have seen so far uses a Nordic semiconductor transceiver chip. And geht denn das hier? Hallo?
Tue ich so. Einfach hier. Ja.
Hmm? Okay. So it's
two examples.
Those are the state-of-the-art keyboard devices. The Microsoft one is was released in 2009, this year, in the middle of the year, I guess. So it's quite new and not that old like the 27 megahertz stuff. So we are not talking about Bluetooth or Zigbee here. It's not wireless LAN. It's based on a technology called shock burst or enhanced shock burst. The Nordic semiconductor NRF 24 family is mostly used in the wireless keyboard devices. I had seen one wireless keyboard device which was a no-name product, and I don't know if they are also using those chips, but yeah, it's most likely to find those chips in every device which is able to communicate over the air, not only keyboards, but also other devices and gadgets. Why are they switching to this proprietary 2.4 gigahertz technique? It's cost saving. Those semiconductor chips costs around $3 for end users, so I guess the cost is quite low. The compact form factor, for example, the antenna is really small and is able to reach devices which are maybe 10 meters far away. So the distance is also it's faster, so we need less transmit time. That means we had less power consumption, which is also a key for this.
What was the statement of the vendors about the time of the battery?
Around 3 years. The battery should stay for 3 years, so yeah, that's quite okay. Wieso geht das nicht?
Das hier ist.
So. Ah, ich dachte, das funkt. Okay.
Noch eins zurück.
So, eins zurück.
Ja.
Well, I don't want to talk a lot about the ShopFirst Protocol, but this is how it looks like. So this is the frame which is transmitted over the air, over the radio link. So we have a preamble which is defined by the ShopFirst Protocol to enable the receiver to identify a valid ShopFirst frame. The preamble is followed by the device address, which is up to 5 bytes. And a minimum of 3 bytes. We have some packet control fields, which are not interesting for us. And we have the payload, which is a variable length payload from 0 to 32 byte. And we also have a checksum, which can be configured to be 1 byte or 2 byte long. Nordic announced the Nordic multi-receiver concept, which is illustrated over here. So, for example, Logitech have the possibility to have one receiver and many devices which are around the keyboard, around the computer, for example, audio devices or keyboards, mouse, beamers, video beamers. So, and one of the NRF 24 transceiver family has 6 pipes for receiving for addresses, those addresses over there. So we can have a multi-receiver which is able to receive those frames for a set of addresses. So this is a disadvantage by using those chips. It's almost transparent to the user. We cannot sniff every ShopFirst frame easily because the devices filter the address, and if the address doesn't match the address which is configured in the pipe, the frame is not processed. So this is the main problem for us. Yeah, and all those different transceivers are all operating on one channel using this multi-receiver concept. So we are almost interested in the payload, which is everything we can see when we, for example, what we did was we opened a Microsoft keyboard, and we used the Microsoft keyboard to build our own transceiver. Yeah, we connected the stuff to our Keykeriki, and yeah, look what we can do with it. So we can only access the payload because the payload is this data which is provided by the transceiver chip, which is connected through the SPI bus.
So the payload basically is what it's transferred independent of the usage of the transmitting device. I mean, you can add other data to it, not only keyboards. So the vendor has now to implement something like a higher level protocol within the payload. And so he has some responsibilities to take care, especially on keyboards. For example,
yeah, the vendor which built the device is responsible for authentication of the device. So nobody wants other guys hanging around with another keyboard and typing stuff like command.exe. So the vendor is responsible for authentication, data protection, and the integrity of the entire computer system. So the USB receiver is the single line of defense, you can call it like this, yeah, because keystrokes, so we are talking about hit devices which sends keystrokes to the computer, so it's almost like sitting right in front of the computer if you are able to send keystrokes. So this is the hardware we saw in the Microsoft receiver. This is the USB dongle. When you open it, you see there's a programming interface. Microsoft programs a fixed address into the devices, so you are not able to add more devices or different keyboards to one of those USB receivers. Yeah, this is the funny thing. I will tell you later. Yeah, this is what we got out of the keyboard itself, and we used the transceiver chip for our own purposes, which that's what you can see there. Okay, so after we were able to receive all the stuff, the next step was to analyze the payload, which is the only thing we can see so far. In this example, we just pressed the A, the B, and the space bar on the keyboard, and we just looked at what is going to transmit over the air in the payload. So we identified something like a sequence ID counter, which is incremented. This is encrypted, so it's not that obvious that it is incremented by 1. We have our encrypted hit code. Yeah, so hit codes, it's like a table. You have your ASCII character, and it's mapped to a hit code using a table. And for example, an A is the hit code 4. A B is the hit code 5. So, and we can see here, we type an A, and we have C9 for a key down event, and this is a key release event, and we have something like a key pressed idle message here, so the receiver is able to identify how long a key is pressed. Yeah, this is the next keystroke, so we have the key B down here, and it's C8. So you can see a pattern. So the A character is a 4 and encrypted at C9, and the B character is a 5 and encrypted at C8. Yeah, that's the first thing you will see if you look at it in the first time. Yeah, and we have a checksum within the payload. It's a different checksum. It has nothing to do with the ShopFirst Protocol. This checksum algorithm is developed by Microsoft, and it's still not clear what kind of algorithm they use in detail, but yeah, we will talk about our research findings here. So this is a bit more compressed. You can see the payload for the key down event for an A and B, C, and 2C is the hit code for the space character. So we found out, if you have a look on this encrypted values, you will see that if you XOR those hit codes which are encrypted, C9, with the value CD, we will get the plain text 4. We can verify this by performing the same operation on C8. So the result is what we expect, the hit code number 5. So it is quite obvious that there's an XOR encryption in place again, but it looks a bit different. They have now not only 1 byte of XOR key, they have at least 10 bytes static key. Yeah. Now we just try to analyze the entire protocol to get an idea how the CRC checksum algorithm works and how the encryption works. We found out that we can generate packets and send those packets when having a correct checksum. Otherwise, the packet is discarded by the receiver. Yeah. So if we use this sequence ID and don't touch the sequence ID of this captured packet and just replay the packet, exchange our hit code, and calculate a new CRC checksum using the static value hex 53, we are able to send packets to the receiver, and yeah, the receiver accepts the packets. This doesn't work for different device addresses, so using a second keyboard with a different device address, this will not work anymore. So we try to find out why. Oh, it's a serious. So, for example, we have a device with the address CD 98350AC0, and yeah, we try to illustrate. This is a packet. The first line is the encrypted original packet payload, and what we have seen is that the key, this is a key down event, right? Is it? No. We take the device address and put them right under this. Yeah, we have the device address 2 times and XOR each character in the original encrypted payload, and we get this plain text, which looks quite okay. So we have some bit fields for meta characters, for example. That's what we have seen in the old technique, the 27 megahertz devices.
So Control, Shift, Alt, that's basically meta keys, yeah?
It's just a bit in the bit field. So yeah, the plain text looks, yeah, well formed. So it makes sense. So we have our hit code right over here, and we have some zeros, and yeah, we have our sequence counter, which is incremented if you have a look on the different plain text packets. Yeah, a few pieces of information are still missing because we don't know how to process those bytes over here. The first 4 bytes, it's still unknown how to proceed with those bytes, and also how to proceed with the single byte right before the checksum, which is the last byte on this packet. So yeah, there are protection mechanisms in place, as you can see. We have an encryption, which is based on the same technique as years ago. Yeah, and we had some challenges in protocol reversing because to find out how the CRC checksum algorithm works, the checksum is obviously built over the plaintext, and yeah, since we are still unable to decrypt the first 4 bytes, we are still not able to build correct checksums. So yeah, what's our challenge? What's next? Since we don't have baseband access using this NRF 24L01 chip, which is in the original devices, we can use a brute force technique to get information about the address of devices in the wireless network. So an advantage of this wireless technique is Nordic Semiconductor implemented something like automatic retransmission on failure. We have retransmission timeouts, and we have an ACK whenever a payload is accepted, and that's why we can also brute force valid addresses to get addresses. If we can configure a valid address in our device, we are also able to sniff, and we are also able to send. So yeah, if we want to brute force the address, we assume that 16 bits of the address space is necessary to increment or to cycle. The addresses are quite similar, and only 2 bytes differs from what we have seen so far. So we have maybe around 23 hours for brute forcing a valid address to sniff and inject payloads in the future.
Because it's a two-way communication, we always get a response when we have the proper address, because we will get an ACK back.
The USB dongle is sending an ACK back,
yeah.
So I got a valid packet, everything is fine.
Another method would be to implement to add a different receiver chip, which allows you to basically directly process the data coming over the air on the signal and read the ShopFirst address right out of the packet. Yeah.
So that was how our desk looked like in the last days. That's a Logitech keyboard, which is over here. It's a quite nice device. It's sad that everything is so broken. Yeah, we have an AES 128 encryption in place. Yeah, that's what we see if we have a look on the payload, which is transmitted by Logitech keyboards. This block is 8-byte encrypted data. So to use AES 128, we might expect 16 bytes encrypted data. So we assume that that the AES algorithm is used to generate a random initialization value for a stream cipher. Yeah. So we have a 4-byte sequence ID, which is verified. We have 4 byte for sequence IDs. We have 1 byte for the checksum. The checksum algorithm is listed below. It's quite simple. So we need the checksum algorithm to generate own payload. Yeah. Using a static encryption key, which must be exchanged between the devices. Logitech states that that the static key is exchanged during the synchronization process, and the key is never transmitted directly over the air. So we recognize several channel hopping sequences in the synchronization process, and we assume that there's an algorithm which we don't know exactly how it works right now, but we assume that we have several small time frames, maybe 500 microseconds, and both devices, the keyboard and the receiver, expect an acknowledge for a packet. So the keyboard expects an acknowledge packet from the receiver whenever they hit. So the keyboard is sending a packet and expects an acknowledge from the receiver. And whenever the keyboard gets the acknowledge, the channel number, which is only a small subset of 12 channels, is maybe used to derive the key. I tried to illustrate the probable key generation algorithm below. So in fact, the static key is never transmitted over the air. It's maybe based on the channels which are hit. Yeah, we don't have so much time, so I
told that already.
Jetzt noch, gar nicht. Zurück.
Okay. You told that already.
Yeah, I already told that. Yeah, so we recognize even if we press the same key several times, the encryption key block is different. So that's why we think that they are using the AES 128 encrypted block for initializing a stream cipher. So we don't know anything about the encryption mode right now. That's what we are going to do the next days, maybe, since we are able to perform replay attacks and perform a more detailed crypto analysis later. It was not able to finish this right now. Yeah, there are also different keyboards we had a look on. Fujitsu Siemens is, it's not worth talking about because it's also plain text and there are no protection mechanisms in place, so we are not going to talk about those.
So you can immediately see the hit codes in the transmitted payload.
Yeah, it's not worth. Yeah, so what maybe the countermeasures for vendors of wireless keyboards and such devices, the usage of cryptographic hardware. Yes, the usage. Microsoft actually use hardware IS chips in their transceivers, but they don't use them. That's a hard part of the findings, so they are still using XOR, and even if they have hardware IS on board. Yeah, limitations from the past. So the one-way communication doesn't apply for today, so we can also perform a handshake and more sophisticated crypto algorithms, public key exchange methods, etc. Yeah. I think we can skip this to have some more time for our demonstration. Last night we tried to figure out how big is the distance to send packets to a computer which has the Microsoft dongle inserted. So we used our Keykeriki. We have an NRF transceiver chip right here, and we connected this PCB using the SPI bus to the existing Keykeriki device. And unfortunately, the battery pack is empty, and so that's why. Du kannst das mal kurz umstöpseln hier.
Yeah. So basically, this Keykeriki now has a hard-coded key sequence, which will be now replied by just applying power to the device. And just let me. Okay,
so here we have a sender, and we try to send some keystrokes. So since we don't have a battery pack right now, I'm using USB to power the device. So that's all. It's no magic. It's just for the power. So now it's on. We wait a few seconds, and we have a command.exe started just for demonstration purpose. Yeah, that's what we wanted to show. And the distance in-house is around 75 meters using this antenna.
Without any further modification on the antenna. So you can see the little red circle. So this was where the transmission was still stable. We could go around the corner as well, but sometimes then signal was lost without further modification. And the packet says about 10 meters.
Nordic Semiconductor told about 100 meters, and we found something in the middle.
We'd like to thank here some guys which actually supported us. That's Nick and Bragg and Eric for helping us in the various phases of that project, and are now available for questions.
2 minutes for questions. Any questions?
Okay.
Yeah,
Thank
you very much.
And thanks a lot. It was very interesting.